Assalamu alaikum wa rahmatullahi wa barakatuh. Today, inshallah, we're going to solve the practice questions on gravitational potential energy and elastic potential energy. Now, the first question, we have 55 kilogram sphere at the top of a slope as shown in the illustration below. At the initial point A, the sphere is 10 meters vertically. So the height here is 10 meters above the final point B, above the final point. So we have here a sphere. We go from point A till point B. The height from here till here is 10 meters. Set the zero level for the gravitational potential energy at point B. So at point B, the gravitational potential energy here is zero. So above this level, the gravitational potential energy will be positive. Below B down will be negative. So up I have positive potential energy, and down I have negative gravitational potential energy. And then find the potential energy associated with the sphere at point A. Now the potential energy, the gravitational potential energy at point A, gravitational potential energy, it's the energy possessed or acquired by an object due to change in its position when it's present in gravitational field. So it depends on the weight of the object, mass, times free fall acceleration, times the height. Here the height is positive because it's above the level that's set to zero. So the mass of this sphere is 55. I'm going to take free fall acceleration 10 times 10. And this will be 5,500 joules. This is the gravitational potential energy at level A. And we know the gravitational potential energy at level B is zero. So the difference between the gravitational potential energy between level A minus B, gravitational potential energy A at level A, and gravitational potential energy at level B will equal 5,500 joules, because at B is zero. Okay, B, repeat the same problem with zero level now at point A. So I'm going to repeat the same problem here. This is A, and the potential energy here, the gravitational potential energy here is zero. The gravitational potential energy here is zero. So I'm going down it will be negative. So the height down will be negative 10 meters. Up, as we agreed, up positive, down negative. It's exactly like you have X and Y. On the X-axis is positive numbers, Y-axis down negative numbers. We're going to do the same thing. Now, what will be the gravitational potential energy? So gravitational potential energy at level A is zero. And the gravitational potential energy at B, we're going to use the same formula, mgh. M is 55, G is 10, height is negative 10. And this will equal negative 5,500 joules. Now, what will be the change in gravitational potential energy? Change in gravitational change, it means difference. So the difference between the gravitational potential energy at A minus the difference between the gravitational potential energy at B. At A is zero, minus the gravitational potential energy is minus 5,500, and this will give us 5,500 joules. Okay, See now, repeat the same problem with zero level. Repeat the same problem with zero level midway down the slope at height 5 meter. So here I have A, this is the point A, and point B. Midpoint, the slope means here in the middle. Okay, in the middle, the gravitational potential energy here is 0. So up, I will have positive 5 meter, and down, I will have negative 5. So the gravitational potential energy at point A, mgh, okay, down it will be negative. I'm moving here at point. I'm moving up, it's positive, down is negative. So mgh here is, here I'm going to call this one h1 and this is one h2. So it will be mg at point A times h1. Mass is 55 times 10 times 5, and this will equal 2,750 joule. Now at point B, gravitational potential energy at point B, mgh2, mg times h2, mass is 55 times 10 times the height down is negative, so negative 5. And this will be negative 2,750 joule. Now the difference between A and B, the change in gravitational potential energy, that means gravitational potential energy at A minus gravitational potential energy at B. At A is 2,750 minus gravitational potential energy at B minus 2,750. And this will give us the same number, 5,500 joule. You see the potential energy, it doesn't matter where we set our zero level, I will get always the same number, the same value for the gravitational potential energy. Now, let's solve another example. I have 2.74 gram coin, which has a zero potential energy at the surface. So here at the surface, the gravitational potential energy is 0, and I drop the coin. The coin is dropped down to a well. So we go down here to a well. The height of this well, h. So since there is zero level here up, I'm moving down, so it will be negative 12.2 meter. After the coin comes to stop in a mud, what is the potential energy with respect to the surface? So gravitational potential energy, write the formula, m mass times free fall acceleration times the height. Mass, it's 2.74 gram. Gram is not SI unit. So to convert it to kilogram, you divide by 1,000 or you multiply by -3. Division, it means multiplication by a negative power. Times G is 10. H is negative 12.2. And you will get negative 0.328 joule. Okay. Let's solve another example. Okay. Here we have the Ukrainian Sergei Bubka. used a short pole to jump to a height 6.13 meter. If the maximum potential energy associated with Bubka was, so I have here the gravitational potential energy, 4.8 kilojoule. Kilo equals times 10 to the power 3 joule. This is the gravitational potential energy. Gravitational potential energy. Okay. At the midpoint of his jump, the midpoint of his jump, that means h will equal the total height 6.13 divided by 2, and this will equal 3.07 meters. At the midpoint, what was his mass? What was his mass? Okay, these are the given. My units, I don't need to convert anything. All of the units is SI units. So the formula, gravitational potential energy equals M mass times T full acceleration times h, mgh. Gravitational potential energy is 4.8 times 10 to the power 3 equals, I don't have M, G is 10, H is a 3.07. So I divide both sides by 10 times 3.07 to give me 30.7, both sides, 30.7. So the mass in kilogram will be 1.56 times 10 to the power 2 kilogram. The last question. The last question, question number 3 and question number 4. Okay. In 1987, Stevka from Bulgaria set a new woman's record in a high jump. It's known that the ratio of the potential energy associated with her at the top of her jump, to her mass was 20.482. So that ratio between the gravitational potential energy and her mass M was 20.482. Okay, what was her height? Now, what is the formula for gravitational potential energy? This is meter square per second square. mgh divided by m. M and m, they cancel out. This equals 20.482. G is 10. I don't have the height. This equals 20.482. So I need h, divide both sides by 10. So divide both sides by 10. Divide by 10, both sides, get rid of 10 here. H will equal 2.0, round the number 5 meter. Okay. Now we're done with the gravitational potential energy. We'll go to elastic potential energy. Now, what is the elastic potential energy? Elastic potential energy is the energy stored in any compressed or stretched object, such as a spring or bungee rope, anything that I can stretch it or compress it. The amount of this energy depends on the spring constant K and the distance the spring is compressed or stretched from the relaxed length. The formula for elastic potential energy we're going to use is half the spring constant K times delta x squared. Delta x is the distance the spring or the stretch string is compressed or stretched from its relaxed length. Now the question says, in 1992, David Ingall of California used a slingshot to launch a dart with a mass. So I have M, let's write the given. M is 62 gram. This one is not SI unit, we need to convert it. So divided by 1,000 or multiplied by 10 to the power negative 3 kilogram. The dart traveled a horizontal distance 477. This is not the distance the slingshot compressed or stretched. It's just the distance traveled. So suppose the slingshot had a spring constant. So K is 3 times 10 to the power 4 Newton per meter. If the elastic potential energy stored in the string shaft just before the dart was launched was, so I have the elastic potential energy 1.4 times 10 to the power 2 joule. How far was the spring stretched? So I need delta X. Delta X. Okay, so here just write the formula and substitute. After we wrote the given, we need to check the units. Now all the units are consistent, all the unit SI unit. So write the formula now and substitute. So the formula again, elastic potential energy equals half K delta X squared. Now substitute. Elastic potential energy is 1.4 times 10 to the power 2 equals half. K is 3 times 10 to the power 4 delta X squared. Now simplify. 1.4 times 10 to the power 2 equals 3 times 10 to the power 4 divided by half. It's 1.5 times 10 to the power 4 delta X squared. Now I need to get rid of 1.5 times 10 to the power 4. So to keep the variable delta X squared alone by itself. So I'm going to divide both sides by 1.5 times 10 to the power 4. 1.5 times 10 to the power 4. Okay, and this is delta X squared. I need delta X, so I have to take the square root for both sides. So delta X will be square root. To get rid of the square, take a square root for both sides. So square root of 1.4 times 10 to the power 2 divided by 1.5 times 10 to the power 4, and this will equal 9.7 times 10 to the power negative 2. Yeah. Okay, we'll solve more question on elastic potential energy. Here we have a spring with a spring force. Spring force is the same as spring constant. Always look at the unit. Newton per meter is a unit for spring constant or a spring force. So this one is 5.2 Newton per meter. Has a relaxed strength. Relaxed strength, it means the strength before we stretch, before this spring is being stretched or compressed. So I'm going to call this one X1. This one from here till here, X1. So X1 is 2.45 meter. Now, when a mass is attached to the end of the spring, here we have a mass attached to the end of the spring and allowed to come to rest, the vertical length now is increased. So here I have a new length from here till here. I have X2 now. X2, the new length, 3.57 meter. So I need the amount of the stretch here, delta X, from here till here. I can find delta X, the new length, X2, minus the old length, X1. X2 is 3.57 minus 2.45, and this will equal 1.12 meter. Calculate the elastic potential energy stored in the spring, the elastic potential energy. So now just write the formula and substitute, like these values. So elastic potential energy equal half K delta X squared. Half K is 5.2, delta X is 1.12 squared. Okay, so if you calculate this one, you should get 3.3 joule. Okay, the last question I'm going to solve, question here number 3. Okay, here we have a 70 kilogram stunt man is attached to a bungee cord with unstretched length. So the unstretched length, the original length of the cord from here till here, this I'm going to call it X1, 15 meter. He jumped off the bridge from a height 50 meters. So the height of the bridge down from here till here is 50 meters. When he finally stops, so the height 15 meters. When he finally stops, he didn't reach the surface of water. He stops here. So here, the stunt man here. The cord has a stretch length of, so this is the new length of the cord from here till here. This is X2. This one is X1. X2, how much? X2 is 44 meters. How can I find the amount of the length that's stretched? This one from here till here, delta X. The amount of length that's stretched, yes. We subtract the new length minus, so delta X will be X2 minus X1. X2 is 44 minus 15, 44 minus 15, and this will be 29 meter. Now the question is, assume that the spring constant of the bungee cord is 71, so K 71.8 Newton per meter. What is the total potential energy relative to the water when the mass stops failing, when the stuntman is hanged here? So at this position, I have two types of potential energy. I have a gravitational potential energy and I have elastic potential energy. So the total potential energy I have elastic potential energy plus gravitational potential energy. Elastic potential energy is half K delta X squared plus gravitational potential energy mgh, mass times free fall acceleration times the height. Now plug the values you have. Half spring constant is 71.8. The length that's being stretched is 29 squared plus m is 70, g 10, and the height from this bridge to the surface of water is 50 times. Now plug these values in the calculator. You should get 3.4 times 10 to the power 4 joule. This is the total potential energy. Okay, I'm going to stop here, and next questions that we're going to solve practice questions.